Hi guys, welcome back to our Chemistry 2 channel. Today we have Emily, Brandon, and Olivia here to share with us the history and evolution of the LCD screen. I hope you guys are just as excited as we are. So before we jump into the bulk of it, I'm going to give you a bit of an introduction. You may be wondering, what exactly does LCD stand for? What is it and how does it work? Well, LCD stands for Liquid Crystal Display. A liquid crystal display is a kind of flat panel display used in digital devices such as digital clocks, device displays, and computers. Just think about the timer you set on your oven when baking cookies, or your dreaded alarm that goes off every morning. Both of those are examples of a liquid crystal display. The display works when exposed to electrical fields. Once exposed to those electrical fields, the liquid crystals then align in a specific manner, similar to the way metal shavings arrange in the presence of a magnetic field. The liquid crystals are liquid chemicals that, once in formation, allow for the passage of light straight through. One of the simpler forms of liquid crystal display is the monochrome LCD. The monochrome display is comprised of two polarizing material sheets that contain a liquid crystal solution in between the two sheets. The liquid crystals then form unique patterns once electricity is applied to the solution. Those transparent or opaque colored crystals create the words or numbers that appear on the display. Pretty cool, huh? I'm not sure about you guys, but before I conducted this research, I had no idea how an oven clock or digital device worked. Now that we know what the liquid crystal display is and how it works, let's talk about where it all started. Believe it or not, liquid crystals date back to the late 19th century, when they were first discovered by Friedrich Reitzer. An Austrian chemist and botanist, Reitzer found liquid crystals in the cholesterol he had withdrawn from carrots. Less than 100 years later, Richard Williams, by applying a voltage, managed to create a variety of specific stripe patterns in a thin layer of liquid crystal material. The researcher's 1962 discovery is understood to be the result of electrohydrodynamic instability within the liquid crystal. Today, that effect is known as Williams' domain. Spanning from 1964 to 1968, George Hellmeyer, Louis Zanoni, and Lucien Barton headed a team of scientists and engineers that, for the first time ever, managed to control the light reflected from liquid crystals. The first ever liquid crystal display was demonstrated. The discoveries made over those 4 years at the RCA David Sarnoff Research Center in Princeton, New Jersey, sparked the beginning of a global industry, an industry now responsible for the mass production of millions of LCDs. The liquid crystal display used by George Hellmeyer used something called the dynamic scattering method, or DSM. The method involved the application of an electrical charge that was responsible for the rearrangement of molecules and scattering of light. However, an improved version created by James Ferguson replaced Hellmeyer's DSM in 1969 because of its inefficient ability to work and immense requirement of power.
Now let's discuss James Ferguson's discovery in more detail. In between George Hellmeyer's DSM and James Ferguson's discovery, German physicist Wolfgang Helffrich from RCA, the same company from which George Hellmeyer emerged, developed the twisted pneumatic LCD based on polarized light and the properties of pneumatic liquid molecules. Now, what does that mean? To answer that question, I will explain Wolfgang Helffrich's thoughts and research, but first I will explain polarized light. We use polarized sunglasses to protect our eyes from sunlight. Sunlight waves vibrate in every possible direction, and polarized sunglasses act as a filter to block out all light waves except for those vibrating in the vertical direction. Light filtered in this way is polarized light. Wolfgang Helffrich sought to improve George Hellmeyer's dynamic scattering mode. In order to understand Helffrich's thoughts, we must first understand the objective of DSM. Dynamic scattering mode consists of multiple voltage-driven steps. Naturally, pneumatic liquid crystals start aligned perpendicular to the two parallel polarized sheets. Pneumatic liquid crystals constitute the liquids mentioned before. Pneumatic molecules are special because they can move around and shuffle past each other, while still all pointing in the same direction. This unique characteristic of always aligning in the same direction is known as pneumatic molecules N-type. Materials that yield the best performance in regards to the N-type are organic compounds known as Schiff's bases, and their pneumatic range is from 83 degrees Celsius to 100 degrees Celsius. In dynamic scattering mode, an external field is applied perpendicular to the plates, causing the pneumatic liquid crystals to align in a direction parallel to the plates. Once the crystals are parallel, the electrical conductivity in the direction along the parallel axis is larger than the conductivity in the short axis directions, causing charge buildup. The induced field and external field generate a shear torque on the molecules, causing them to move in a circular motion. The external field is further increased, and the molecules go into a mechanically unstable turbulence. The molecules can then randomly scatter the light incident on them, causing a milky white appearance. Although Hellmeyer's DSM succeeded in strengthening the incident light intensity, it required a great deal of applied voltage. Wolfgang Helffrich had a brilliant thought. He asked himself, would it be easier to modulate the intensity if there were a natural or induced twist in the liquid crystal? Helffrich tested his theory by creating parallel troughs. He applied a thin film of compound on glass substrates in parallel rows, thereby creating troughs for the pneumatic liquid crystal molecules to adhere to. The properties of the pneumatic liquid crystal molecules would cause the long axes of the molecule to attach to the glass surface in the direction of the trough. Two troughs perpendicular to one another would be fixed on opposite interiors of the polarized sheets. The troughs would create the induced twist. Helffrich then assembled his mechanism, and it operated as follows. Incident light is linearly polarized when it passes through the first polarized sheet. The plane of polarized light then rotates due to the induced twist of the liquid crystal molecules. As the polarized light reaches the second polarized sheet, it has been rotated 90 degrees from the position of the first polarizer, and it is able to pass through the second polarizer unimpeded. Helffrich called his mechanism the twisted pneumatic display. The intensified incident light produced is considered the normal state for the twisted pneumatic display and requires no voltage to maintain. In regards to image display, an applied electric field could allow for extensive precision control of phase retardation, meaning different light intensities could be controlled to provide a fine grayscale for image display. Hellmeyer was Helffrich's supervisor at RCA. When Helffrich presented his research to Hellmeyer, Hellmeyer criticized the prototype and expressed disinterest. The RCA management unfortunately terminated the liquid display research group, and Helffrich left RCA to join Hoffmann-La Roche in Switzerland. At Hoffmann-La Roche, previously mentioned, James Ferguson developed and patented an alternative version of Helffrich's same idea. Today, Helffrich, his collaborator Martin Schadt, and Ferguson are jointly credited with inventing the modern liquid crystal display.